Say we're asked to determine how three planes intersect. Well, the first thing I would do is check the normal vectors of each plane. Again, the normal vectors can be found by looking at the coefficients of the x, y, and z values in your general form equation. So this first plane will have the normal vector 1, 1, 1. The second equation will have the normal vector 2, 2, 2. And this third equation would have the normal vector -3, -3, -3. Now, if all three of these normal vectors are multiples of each other, that means that the normal vectors are collinear or parallel to one another, and that means that the planes themselves are also parallel. So in this case, you can see that if I multiply this first vector by 2, I'll get the second vector. If I multiply that first vector by -3, I can get that third normal vector. So these vectors are in fact scalar multiples of one another, so these three planes are all parallel. Now, the first two planes are actually the same plane, and I can say that because if you multiply the entire equation by 2, you get this second equation. So those two planes are actually something like this, where they're the same plane. And you can see as I flip back and forth between those two planes, I can't show both at the same time because they are one and the same. They are located on top of each other. This third plane, however, the entire equation is not a scalar multiple of the other equations. If this 50 value was a -3, it would be. And so what that means is that that third plane is parallel to the other two, but it is not the same plane. It has some distance between it and those first two planes. So hopefully that makes sense. So that's the first thing I do. Okay, I take a look at those normal vectors and I see if they're all the same. Now, most of the time, all three planes won't be parallel. It is possible that when you check your normal vectors, that 2 of the 3 normal vectors are parallel. And when that happens, it means you have 2 parallel planes, and that could look something like this. Right? You could have 2 planes that are parallel, and you could have a third plane that intersects both of them, and it could intersect each plane at a line. You see these orange lines here. Now, the third scenario, and this is the one that's most interesting to me, is the one where none of the normal vectors are multiples of each other, and that means that none of the planes are parallel to one another. And 3 things can happen. You can either have the 3 planes meeting at 3 separate lines, like this here. You could also have the 3 planes meeting at one line, like this. You see how they all intersect at a single line. Or you could have all 3 planes intersect at a point. And this is very interesting, right? So there's only one point you can see here that exists on all 3 of these planes. So there are lines of intersection between pairs of the planes, like this plane and this plane meet at this line here, but there's only one point where all 3 of the planes meet. So let's do an example. Let's say we have the plane x plus y plus z plus 1 is equal to 0. Let's say we have another plane. We'll use 2x plus y plus z minus 2 is equal to 0. And we'll use x minus y plus 2z plus 1 is equal to 0. And I'm going to label these planes. This can be plane A, plane B, and plane C, just to help me stay organized. Now, what I want to do in this question is figure out how these planes are intersecting one another, if they are at all, right? And one thing you can do is you can look at the normal vectors. The normal vector for this first plane would be 1, 1, 1. The normal vector for this plane would be 2, 1, 1. Okay, those are not scalar multiples of each other. And over here you have 1, -1, 2. So it should be pretty obvious just by looking at these that none of these planes are going to be parallel to one another. So we don't have to worry about that. So let's try to solve for the intersection, whether it's a point or a line or multiple lines, we don't know yet, but let's try to solve this system of equations. Now, If you do this on your own, your solution might look slightly different than mine, that's okay. But the way I'm going to do this is I'm going to start by adding plane A and plane C. So A plus C. And the reason I'm doing A plus C is because y here has a coefficient of positive 1, and the y here has a coefficient of negative 1. So if I add those two equations together, my y values will be eliminated. And I'm actually going to use elimination here. So x plus y plus z plus 1 is equal to 0, plus x minus y plus 2z plus 1 is equal to 0. So I'm doing elimination. I'm adding these two equations together. X plus x is 2x. Y minus y, like we said, that's going to be 0. Z plus 2z is 3z. 1 plus 1 is 2, and that's equal to 0. So what I have here is 2x plus 3z plus 2 is equal to 0. Okay, fantastic. That's my first equation. Now let's do another elimination. I already used equations A and C. Next, I think I'm going to do B and C. Now, why would I add B and C? Because once again, if I do that, I will eliminate these y values, and I'll get a second equation that has just x and z remaining. Just like how this only has x and z remaining, I'll get another equation that has just x and z remaining, and by doing that, I'll then have two equations with two unknowns. I can continue to solve the system. So, like I said, I'm going to do B plus C. I'm going to write it here, 2x plus y plus z minus 2 is equal to 0, and x minus y plus 2z plus 1 is equal to 0. I add these equations together. 2x plus x is 3x, plus y minus y plus 0, z plus 2z plus 3z, negative 2 plus 1 is minus 1, is equal to 0. So all in all, we have 3x plus 3z minus 1 is equal to 0. So using these two equations that I got, I can now figure out what x and z are equal to. So I'm going to do 2x plus 3z plus 2 equals 0, and I think I'm going to subtract 3x plus 3z minus 1 is equal to 0. And the reason I'm subtracting these is so I can eliminate these z terms. 3z minus 3z will give me 0. That's what I'm trying to do. So 2x minus 3x is negative x. 3z minus 3z is 0. 2 minus negative 1, that's the same as 2 plus 1, or 3. That equals 0. Solve for x. You'll get x is equal to positive 3. So I've solved for my first value between x, y, and z. I got x. Now let's solve for z. I already have equations that have z and x in them. Let's use this one here. So 2 times x is 3, plus 3z plus 2 is equal to 0. Let's solve for z. This will be 6 plus 2 is 8. Move it to the other side. 3z is equal to negative 8. In other words, z is equal to negative 8 over 3. So I now have my z value as well. Now all I have to do is figure out my y value. I need an equation that has x, y, and z in it. Why not just use the first one up here? Equation A, x plus y plus z plus 1. So x we know is 3, plus y plus z we know is negative 8 over 3, plus 1 is equal to 0. Let's solve for y. If I keep y on this side of the equation and move everything else to the other side, 3 and 1 together is 4, so minus 4. I have my positive now, 8 over 3, because it's moving to the other side. I can rewrite this so there's a common denominator, so instead of negative 4, I can put negative 12 over 3 plus 8 over 3. And if I do that, I should get negative 4 over 3. That is equal to y. So I now have all three values, x, z, and y. Because I got a unique value for each one, that means that the point of intersection, it is a point, right? The point of intersection, it's a point because I got a unique value for x, for y, and z. I got a number for each one. This means that my point of intersection is 3, negative 4 over 3, negative 8 over 3. This is the point of intersection, and as a matter of fact, you can look at it here in 3 dimensions, and you'll see that orange point where all 3 planes intersect one another. So you can see there's a line here where these 2 planes intersect. There's a line over here where these 2 planes intersect, and over here as well. But there's only one point where all 3 planes are going to intersect. This point that we found exists on all 3 planes, and it's the only point that exists on all 3 of these planes. So if you took this point and you plugged it into any of those 3 equations we started with, the equation would be balanced. And you can do that for each plane if you wanted to check your answer. You could plug this point into each equation and make sure each equation ends up being 0 equals 0 once you simplify it. Okay, let's do another example. Number 2. Okay, let's say we have the equations x plus y plus 3z plus 1 is equal to 0. We also have negative 5x minus 5y plus 3z minus 5 is equal to 0. And we have 4x plus 4y plus 6z plus 4 is equal to 0. Again, look through the normal vector, see what it would be. In the first case, it's 1, 1, 3. In the next one, it's negative 5, 3. And in this one, it's 4, 4, 6. So hopefully you're able to tell just intuitively that none of those normal vectors would be scalar multiples of each other. If you have to write them out separately and try to look at it that way, you can, but it should be fairly obvious that those are different normal vectors, and therefore these 3 planes are not parallel to one another. Now let's do some elimination and see what we get. Again, I'll name all of these planes, plane A, plane B, plane C. And I think I'm going to start by doing plane A minus plane B and then cancel out those Z values in the process. So A minus B is what I'm doing here. So x plus y plus 3z minus 1 is equal to 0 minus negative 5x minus 5y plus 3z minus 5 is equal to 0. Just like that. Remember, I'm subtracting all of this. Don't forget about that negative sign. X minus negative 5x. That's like saying x plus 5x, which is 6x. Okay. Y minus negative 5y. Same thing. Plus 6y. 3z minus positive 3z is 0. Plus, oh, sorry, there should be a plus 1. I don't know why I wrote negative 1. It's coming from here. It should be a plus 1. Plus 1 plus 5 is plus 6. There we go. And that equals 0. So 6x plus 6y plus 6 is equal to 0. And you could actually divide both sides of this equation by 6 and simplify it a little bit. You'd get x plus y plus 1 is equal to 0. That's absolutely allowed as long as you divide both sides by the same number. So that's my first equation I've come up with. Now, in that process, I eliminated z, so I would like to eliminate z in my next elimination as well, just so I have 2 equations with x and y. And I think for this one, I'm going to use equations 2 and 3, but what I'll have to do is I'll have to multiply this second equation here. I said 2 and 3, I should be saying b and c, but I should be multiplying equation b by 2 so that this becomes a 6z, and I can eliminate these. So yeah, what I'll do is I'll say 2b, so 2 multiplied by equation b minus equation c. That's what I'm going to do here. So 2 times equation b, that gives me negative 10x minus 10y plus 6z minus 10 is equal to 0. And then I'm going to subtract equation c, which is 4x plus 4y plus 6z plus 4 is equal to 0. And now I'm going to subtract. Minus 10x minus 4x is minus 14x. Minus 10y minus 4y is minus 14y. 6z minus 6z is going to be 0. That's what we want. Negative 10 minus 4 is 14, and that equals 0. 0 minus 0 is 0, right? So I have negative 14x minus 14y minus 14 is 0. I can divide both sides of the equation by negative 14, and I would get x plus y plus 1 is equal to 0. Well, this is quite interesting. So over here, I get the exact same equation as I get over here. What does that mean? Well, it means that if I were to try to solve the system of these two equations, right, I would get something like 0 is equal to 0. Let me show you what I mean. You take this first equation, x plus y plus 1 is equal to 0. You take the second equation, x plus y plus 1 is equal to 0. You try to do an elimination by subtracting, you end up getting 0 is equal to 0. If you have something like this, this is what we call a dependent solution. Okay, dependent solution. Therefore, we would say that these planes must be intersecting at a line. Okay, if you get something like this, dependent solution, it means there's a line of intersection. So how can we find what that line of intersection is? Well, you can take the equation that we found, the x plus y plus 1 is 0, and you can isolate it for x. You can say x is equal to negative y minus 1. And so what I've done is I've expressed the value of x in terms of y. Well, you can do the same thing for all your variables, right? You can express y in terms of y. You can also express z in terms of y. Now, how would I do that? Well, look at that first equation we had. The first equation was x plus y plus 3z plus 1 is equal to 0, right? If I substitute in these values for x and y in here, you can solve for z, right? You would have negative y minus 1 plus y plus 3z plus 1 is equal to 0. What happens when you simplify things here? Minus 1 and plus 1 cancel out. Minus y and y cancel out. You're left with 3z is equal to 0. Divide both sides by 3. You get z is equal to 0. So we have these three equations. These are actually your parametric equations of the line, right? If you say let y equal t, then you'll have x is equal to negative t minus 1, or you could write it the other way, right? You could say minus 1 minus t. For y, you just have y is equal to t, right? Or you could say 0 plus t, if you want to include that 0. And for z, it's just equal to 0, or you could say 0 plus 0t, just to remind you of the position vector and direction vector. You don't have to write them like this. You could just say this is t. You could just say this is 0. That's all right. But I'm going to write them like this just to make my point. If we take that information, we can make a vector equation of the line, and you would get negative 1, 0, 0. That's your position vector from these three values. And then you would have plus t multiplied by negative 1, 1, 0. Right? From these three coefficients. There's a negative 1 in front of this t, a positive 1 in front of this t, and a 0 in front of this t. So you have your position vector and your direction vector. So this is the vector equation of the line where these three planes intersect one another. And if you want to take a look at what that looks like, you can look at this diagram here. I've actually plotted all three of these planes, and you can see the orange line there. That is the line that we just found the equation for. That's where all three of these planes intersect one another. Okay, let's do another example. Example 3. Say we have the planes x plus y plus z plus 1 is equal to 0. We also have x plus y plus 2z plus 3 is equal to 0. And we have x plus y minus z plus 5 is equal to 0. And again, I'll label these A, B, C. We'll do some elimination. Let's start by doing A minus B. If you do A minus B, x plus y plus z plus 1 equals 0 minus x plus y plus 2z plus 3 is equal to 0, you're actually going to be able to eliminate two variables. X minus x is 0, y minus y is 0, z minus 2z is minus z, 1 minus 3 is negative 2. Solve for z, you'll get z is equal to negative 2. Okay, so that's a value of z we got. Cool. Now let's try to do another elimination. What if we did a minus c? What would happen here? A minus c. Well, we would have x plus y plus z plus 1 is equal to 0 minus x plus y minus z plus 5 is equal to 0. X minus x is 0, y minus y is 0, z minus negative z is 2z, right? Because it becomes z plus z. So you have 2z there. 1 minus 5 is negative 4. That's equal to 0. And if you solve for z, you get z is equal to positive 2. Okay, well, hang on a second. We already said that z must be equal to negative 2. If you get two different answers for a variable, this is what we call an inconsistent equation, right? Or an inconsistent system, I should say, because z is equal to z, right? We know z is equal to z, but that would mean that negative 2 is equal to positive 2. And negative 2 does not equal positive 2. We know that's not true. So that's why this is called an inconsistent system. And what that means is that there's not one solution, right? It's not one line of intersection. It's not one point of intersection. Rather, it's three separate lines of intersection. And if you want to see what this looks like, you can take a look at this diagram here, and you can see that there's 1, 2, 3 lines where planes are intersecting, but you only ever have 2 planes intersecting at a time. You don't have any location, whether it's a point or a line, where all 3 planes intersect. It just does not happen in this scenario. Again, that's what we call an inconsistent system. Now, if you wanted to find the equations of each of these lines of intersection, you could absolutely do that. You would just have to use the 2 equations for those 2 particular planes and go through the process of finding the line of intersection, which I've highlighted in this video here. You can go check that out if you're interested. Okay, so now we know all the possibilities of how 3 planes can be interacting with one another, whether they're parallel, whether they're intersecting at one line, several lines, or at a point.